Houdini provides whitewater nodes allowing us to easily create whitewater for flip fluids. You can use a .NET to simulate whitewater using the Whitewater Solver and Whitewater object nodes. The way whitewater sims work is by building on top of the flip simulation. So you need to know the basics of flip sims. If this looks familiar to you, you're all good for the flip fluid. And in order to render the whitewater, I use both the whitewater particles and create a volume for the whitewater for rendering. So it's nice to know how to set up a simple volume material as well. However, the volume material is optional. The whitewater looks just as good without it, but it adds an additional look to it. If you need a refresher in one of these two topics, I have previously created videos in the past in preparation to build up to this one. For a refresher on flip fluids, you can watch Flip Tank Basics for Beginners in Houdini. I continue straight off this video reusing the same scene file and reuse the same flip sim. I add whitewater to the flip fluid sim demonstrated in this previous video. However, if you know the basics of the flip fluid, you're more than fine, because you only need to know the basics. For volume material, I created a video that describes the process in setting up a simple volume material. You can check that out if you need a refresher. But I find that the whitewater looks just as good rendering only the particles. Especially if you're doing a far shot, the whitewater volume won't even show. But rendering the whitewater volume adds an additional subtle look to it, but it's optional. Links will be posted in the description below. This is the flip fluid simulation setup that I have demonstrated in previous videos that I'm going to be using to build on top of in order to generate the whitewater, because the whitewater builds on top of the flip fluid simulation in order to calculate where to put the whitewater particles. So since this video is only focusing on the whitewater, I'm not going to be diving into detail about the flip fluid setup, but I will need to go into the flip fluid and show you what we need to extract from this flip fluid simulation setup in order to feed it into the whitewater simulation. The whitewater has two parts into rendering that I have used. One is the particles, so that's these little bubbles you see here, and another one is this little gas-like look that is appearing inside the fluid. I'm gonna turn off the particles. It's this gas-like fluid. Actually, I will turn up the intensity of this so you can see, just to show it. I think it's a little bit more clear. This is the volume material set up for the whitewater. So I'm going to turn it back down. And this is the particles. This is just the particles. As you can see, with just bringing the whitewater particles, it looks really nice already. The whitewater volume is optional. You don't really need it unless it's an additional look to it if that's what you want. But it does require you to know how to set up a volume material. And you can check that out in one of my previous videos. I'll put a link in the description. So I'm just going to turn that back on. So let's go into the flip simulation first. So this is our basic flip simulation that you've probably seen in one of my previous videos. This is a direct use, reuse of the scene file from that teddy bear flip tank where I dropped 3 teddy bears into a cube of water. The flip simulation looks like. So this is just during a flip with the closed flip tank. Now we have that a flip simulation.net here. Then we have our .io where we extract all the information from the flip fluid simulation and bring it into this context. Then we put in that fluid compress that compacts all that data, so it's in a nice in a more compact format. I throw down a file cache because I don't want to be recooking the entire flip fluid simulation all over again every single time. Then I put down a null node right here, so I know that this is what I need. This is what I will be needing to bring into the whitewater simulation. This is the data that we need. So you can, by throwing down this null here, it's easier to find. So let's go to the whitewater. So in the whitewater, I have my object merge, so I bring in that fluid compress. That was the node that I showed you before. That was this node. We need to bring in the flip fluid simulation data into the whitewater. So I bring it, all that flip sim data, into this context. Then there's something called a whitewater source. So the first input of the whitewater source is for the liquid simulation. That's our flip fluid sim. I plug in all that sim data into the left input of the whitewater source. It is always a good idea to put down a null node to indicate what it is. So this is just for organization. Then when we have our .NET, because the whitewater uses a simulation to generate all the whitewater particles, we have our regular .NET. And inside the .NET is very simple. We just have a whitewater object, and like any other .NET, there's always a solver. So we have the respective whitewater solver. Now, I don't think I changed anything in the whitewater object. It's just the default. In the whitewater solver, for the emission source, we need to feed in a whitewater source that we created over here. That's this node. So that's where we convert the flip sim data into whitewater data that we need to feed into this whitewater source, a solver. That's what goes into there. Now for the whitewater solver, in the limits tab, there's a closed boundaries, limit size, and limit sensor. So this will look very familiar to the flip fluid solver volume limits. In fact, this is actually directly linked to it. Actually, I'll show it to you. Just gonna open this up. I'll throw this over here. The flip fluid, this solver, which has this flip solver volume limits. It has a box size, box center. So these values are actually linked to this box size and the box center. And this closed boundaries is linked to this flip object closed boundaries. These are all linked. The reason behind that is because the flip solver volume limit size, this limit size defines where the water is in the simulation. Anything outside this volume limits, the flip solver won't care for. The flip solver won't apply calculations to anything outside this volume limit. So wherever we have water, we probably want whitewater particles. That's why these two limit sizes these parameters have to be the same. So back to the whitewater solver. In the foam, if we scroll down, there's a repellent. I have enabled the repellents. So what this means is, when this is enabled, the whitewater will repel itself. Particles of the whitewater will start repelling itself, so the whitewater will look like it's more spread out. Now, I've cached out a simulation of the whitewater where the repellent is enabled and one where it is disabled. So you can take a look at what it looks like. The whitewater simulation is quite simple. That's basically it. I didn't change, and I don't think I changed anything else. Then we drop down a .io for the whitewater in order to extract all the whitewater simulation data outside and bring it into this context. Because the whitewater is still a simulation, we still need to extract all the data. So I'm just going to walk you through this. So this is the node that I'm going to be using to extract all that simulation data. It requires a DOP network, so we're going to just click and drag the DOP net into it. And the DOP node, well, that's going to be our whitewater particles, whitewater object. So in here, I'm going to search for this context, objects, whitewater simulation, and it's inside this DOP net. So DOP net, whitewater object is what we want. And then I don't need to import the simulation settings. and I choose particles to import the geometry field. So I cooked a few frames out. So this is what it looks like. This is the whitewater particles being generated by the whitewater solver. Now I don't need this because I pre-cooked a version out so you can see it. So I'm just gonna play this out. So that's what it looks like with the repellent enabled. In the whitewater solver, the foam tab with the repellent enabled, this is what it looks like. Oh, sorry. Here we go. So it's quite dispersed, as you can see. It spreads out a bit. So I pre-cooked a version with the whitewater disabled. So I'm gonna put this here. And I'm gonna... So this one doesn't... the whitewater doesn't disperse as fast. It sort of clusters together. And it slowly grows out, sort of. Compared to this. This is with the repellent enabled. And this one is with the repellent disabled. So you can see a huge difference. Now right after you import all of the whitewater simulation data into this context through the .io, and then it's a good idea to put down a file cache so you don't have to recook the whitewater simulation every single time. And you can have faster playback. Otherwise, if I put it here, if I put the render flag here, it'll start cooking. It'll start cooking, and it does take a while, but this is pretty fast. It's a good idea to put down a file cache. This right here will give you a lot of particles. You can actually just render the particles right here, like right now, out of here. So I'm going to put the render flag here. I have made a separate geometry node to render out the whitewater particles. So in here, I put down an object merge, which I bring in that particle null data, which is this, which is just bringing in this into this context. Now you might think, why would I do that? It's because this is a lot easier. In this geometry node, there's a Redshift object parameter tab. In here, in the particles, check the render object as particles. Otherwise, you won't be able to render it with Redshift. And then I turned down the size of each particle. So I'm going to turn off the whitewater sim. Enable this. So this is what the particles look like. And this is rendering straight off what comes out of the whitewater sim data. And it looks decent. Okay, for the whitewater particles here, I'm going to change this over to this other material I have set up. Render this. This looks a lot brighter. But what I wanted to show you, this material is very simple. It's just a white, literally just a constant, a white constant feeded into the surface. Then you get this, which isn't too bad. If you want something simple and you want something fast, you can get this. Now let's go back to the whitewater simulation. Right after the file cache, I throw down an attribute wrangle. This attribute wrangle node, which is named set density, is something I learned from the whitewater shelf tool. I explained the shelf tool in a different video. Again, a link will be in the description. In sidefx's Whitewater Shelf tool setup, they had a similar set density node that calculates the density data using attributes like the age, foam location, and depth that are all given by the Whitewater solver, and use all this information from the solver to calculate new data, the density, which wasn't given by the Whitewater solver. Now, my version of the set density is a simplified version compared to the one sidefx used in their Whitewater Shelf tool. I only used the depth and a ramp to drive the values of the density. This was good enough for me, but maybe because my project scene is a very simple one. I will be providing this Houdini project file to you for download, so you can get the set density node through that. A link will be in the description. I use the depth attribute given by the Whitewater solver to calculate a new density attribute. And we all know when you have density, we can create a volume from that density. I convert the density into a volume by using the volume rasterize attributes. Under the attributes, you can then feed in the newly calculated density attribute, and it'll create a volume for you. The volume is created based on the density attribute that we fed into it. This way I get a density volume. So you can then render out this density volume after you assign a volume material to it. That's to get this. Then I throw down a null node and apply the render flag to this, to right here. Remember to put that there, otherwise it won't render. As for the out particles, I'm gonna connect this back over here because I only connected it up here to show you what it looks like when you render out just the particles. The set density node is completely optional. You don't have to have it. By rendering just from straight out of the Whitewater sim data, you get pretty good results, which is this straight out of the Whitewater sim data without the density attribute. To render the particles in Redshift, remember to enable particles for rendering by going to the Render tab, Particles tab, check the render object as particles, then adjust the size of the particles. And this material, this Whitewater particle material, is just a plain white color. Just white color plugged straight into the surface. But since we have calculated the density, I'm going to be showing you how the volume material looks like. We use the density to set up the material for the Whitewater particles. So I'm going to connect the density over here. I'm going to go back up and have different material set up for this. Particles. So it's a little, you can see a little gradient. The ones with higher density values are more, appear more brighter white color. So let's look at the Whitewater particle materials. Now I prepared another one and another one just to show you for demonstration purposes. So let's go into this one. Let's render this first. That's this one. Now this has a lot of color to it. We can actually ignore this material. So I bring in the density, the alpha, and the depth. So I brought that into this material, and you can, these attributes are using the attributes that come from the Whitewater simulation. These two come straight out of the Whitewater simulation. This one is calculated by that set density attribute render node. The interesting one that I want to mention is the depth attribute that comes straight out of the Whitewater sim. Now, how does the depth attribute work? Let's look at what we got here. So the depth attribute, we have particles that have depth of 0.82 ranging to negative 0.82. As you can see, most of them are negative. There's only a handful of them. So we're right here. It starts, the depth values start to become negative, and we're only just a teeny bit scroll down. So that means all these particles up here and on this scroll bar are all positive values. Most of the particles, whitewater particles, are all negative depth values. So it's safe to say that the ones up here, appearing at the top or coming away from the particle fluid, is plus depth. The ones that are inside the fluid are negative depth. So that's where we get the depth value comes directly from that. But this is not very useful for us when we're setting up the material because our color ramp is 0 to 1. Now this is 0.8 up here, positive 0.8 to negative 0.8. So that's not very useful when we're setting up a color ramp for that. So we need to throw down a math range and sort of remap the depth into a 0 to 1 value that we can use for the ramp, for the color ramp. So this math range is ranging from negative 1 to 1. Now you might think, why am I using negative 1 to 1? This is starting from negative 0.8 to 0.8. Well, that's because we're on frame 105. If we go to a different frame, if I go to 62, the depth range is a little bit different. It starts off with negative 0.7. Highest is 0.7. Lowest number is still negative 0.8. But what I'm trying to say is that the depth range will be different depending on which frame you're on. But we know that it's always between negative 1 and 1. Well, actually, it should be always in between negative 0.8 and 1 because this is a closed tank. This is a closed flip fluid. It's never going to be deeper than negative 0.8. This is unless water is falling through the tank. So I use negative 1 to 1 to make the math easier and remapped it to 0 to 1 and plugged it into color ramp. So you can see the highest value here is purple. But we don't see any purple. There's no purple anywhere. And then yellow is 0.5. It's halfway in between here. Halfway in between this ramp means that it is the original depth value is 0 because this is the original range. So that's why I stuck with negative 1 and 1. It makes the math a little easier to calculate. In between this, the midpoint of this ramp, this is 0 to 1, is actually the remapping from the original depth value of negative 1 here to 1 here, which makes the midpoint here 0. The original depth value is 0 right here. Now, most of these particles are red, so they're right here. We know that they are right, has a value, remapped value of 0.1. It's in between. It's best don't pay too much attention to this value. Instead, think about it this way. It's red, so it is in between the white and yellow. That means the depth is in between the white and yellow. Well, I don't see much white. The white is actually, it's whitish, like this is the whitish. I'm going to exaggerate this a little bit more by making the particles a little bigger because my particles is too small right now. I'm gonna pick a different frame. Okay, this is a good frame. I'm gonna 0.5. So this is a bit more clear. This is only for demonstration purposes. So now we know that the 0 mark, the depth value in the middle, is yellow. And as the depth value decreases, so the more negative the depth value gets, it gets red and then whitish. That's why this red here is the deepest, and then it's a bit lighter over here. Now, why is that? That it seems a little odd because depth, okay, if we're getting deeper downwards, why is this yellowish. Why is this a little yellowish? The depth is the distance between the whitewater particles and the fluid surface. Since this is a cube of water, there is water surface on the sides as well, and that's why the whitewater particles is a bit yellowish on the side, because the particles is getting closer to the surface of the water on the side. My flip fluid tank wasn't blocking the teddy bear from dropping from the sides. The fluid stays within the tank. However, when the flip fluid simulation calculates where the teddy bear kind of rolls out on the side, a bit of water is lost when the teddy bear falls out of the tank, and I believe that's what's causing this unwanted hold on the side of my flip tank. If I wanted to improve on the flip fluid simulation and get rid of this hole or this divot point in the water fluid, I would increase the particle separation and increase the resolution of the flip fluid simulation, because my teddy bear dropping into the flip fluid simulation was cooked under a very low res simulation. It was 0.1 particle separation, and the sub steps for the flip sim was very low as well. The sub steps, I only used 2. So 1 and 2. The minimum sub steps is 1 and the max is 2. So this is a very low res sim. And a particle separation of 0.1, which is really low res. If I wanted a more higher quality flip fluid sim, I would need a smaller number, like 0.007 or something. But it takes really long to cook. So for time constraints and the filming purposes, I use 0.1. That's how I ended up with a hole that ended forming on the particle fluid surface on the side. If I wanted to produce a more accurate flip sim and generate better whitewater particles, because you have to remember the whitewater particles build on top of the flip sim. Whatever happens to the flip sim, that effect will ripple down to the whitewater simulation as well. That's something you need to be aware of. For this particular scene I have here, the teddy bear scene, it's relatively a simple scene, and the defects probably doesn't show as much. But if you're producing something for a blockbuster movie scene, it might not be that great. But what I wanted to point out is that the depth is calculated, is the distance between where the fluid surface, so the fluid surface, and how far the particle is inside the fluid. So all the particles, all the whitewater particles that is inside the flip fluid is negative, has negative value. The ones at the top here, this is yellow, because this is getting close to the fluid surface. And the one at the side here is getting yellowish. So it's getting a lot lighter. It's in between here. That's where this yellow comes from. So I'm going to go back to the object node. I'm going to turn this back down. The material, I'm going to assign it back to the whitewater material, particle material I had. The other one, the red yellow material, was only used for demonstration purposes. So this is the actual whitewater particle material I've used. Inside, I'm gonna take a look. So this is actually using the depth attribute in order to get the bubbles. So you can see here that the bubbles are brighter white color, and it has a gradient. It dims down to a greater darker white, darkness. So this is, I kind of like this cool effect. As it gets deeper away from the fluid surface, it gets a bit more darker, a bit more brighter. I like that effect. This can be anything you want. Like if you didn't like this, you can change your color ramp. This math range is exactly the same as I used in the debugging mode, where I showed you just now, as ranging from -1 to 1, and it remaps it to a 0 to 1 range in order to, so it would fit on the color ramp. In the color ramp, I just have black and white, and I moved the white all the way down because I wanted this to be more brighter white. let's go back up here. I'm going to turn off the particles for now, and I'm going to go over the whitewater volume. So the reason you don't have to do this, it looks pretty good without the particles, but if you do want to know how I rendered out the volume, so this set density node here will calculate the density values for us. I then use the newly calculated density values and feed it into the volume rasterized attributes node, which will generate a volume for me from the density values. Throw down the null. This is what I'm going to be rendering. So in this node here, for our render, we need a volume material. So I have one set up right here. Now this is just the Redshift volume material. I plugged into the density in here. I turned up the coefficient. I'm not going to be going over a lot of detail of the Redshift volume material because I explained a lot of that in a previous video on how to set up a volume material for Redshift. So I'll provide a link in the description below. For the absorption, the higher this value, the more thicker the volume will render out. By lowering this, the volume will become more transparent, more light will be allowed going through it. If I increase this, it gets, the cloud, the smoke gets gas-like, it gets more thicker, less light is allowed through it. But you can see it more defined. I explained this in a lot more detail in the volume material video. I wanted gas like whitewater to show more clearly, so I did turn this down for that reason. I wanted light to go through past it. And I think that's all I changed. So this is how we use. So I only used the density to drive the whitewater volume material. That's how I got this little steam gas-like look inside. And when combined with the whitewater particles, it looks like this. You can be the judge of whether it's worth it or not to add the gas-like whitewater volume effect to your project. It's quite a lot of work to add in just the volume effect. You need to calculate the density, convert it to a volume, and set up a volume material. But the settle effect can be quite satisfying. This Houdini project file will be available for download, link in the description. It will not include the Redshift materials because it goes against the user agreement to share those. I will, however, leave sticky notes on the parameter values I've used to set up the respective Redshift materials so you can recreate them with ease. And also, a deeper explanation of the math behind the set density node will be posted on a website, link in the description. Thank you for watching and sticking to the end.